Hello everyone, how you going? Welcome to the James Webb Space Telescope Explained. Now obviously it's just an incredible piece of technology that was launched and then took a while to get to its particular orbit, but now it's just kind of cruising along, so let's just see what it's all about.
In the beginning, our universe was very hot and dense. As the universe cooled down, the electrons interacted with the nuclei, forming the first atoms. A few 100 million years later, the first stars and eventually galaxies appeared. But how did they form? This thing will help us understand. A $10 billion time machine, which has been in development for over 20 years.
Wow. I honestly forgot that it was $10 billion that it took to get it off the ground, or I guess more so than off the ground, just all the way into space. But no, $10 billion? I mean, I guess on the other end of the spectrum, it's not that much money, all things considered, because in space, things just get very, very expensive very, very quickly. I think, what was it, going to the moon was like $250 million or something, adjusted for inflation. And so when you put 10 billion next to 250 billion, it kind of looks a lot more reasonable, and you go, oh, why don't we just make more of these things? I mean, if it's going to be that life-changing and tell us what all the background radiation was from the beginning of time, then just pump them out. But no, like he said, 20 years worth of research and development went into making this, and so let's just figure out more about it.
Imagine that you are 65 million light years away from Earth, somewhere in the Virgo cluster, and you have a very powerful telescope which you can use to study the Earth. Taking a look through the telescope, you would be able to see what dinosaurs looked like on our planet.
Yep.
Of course, we will face many obstacles along the way, but we are talking about an incredibly powerful telescope, right?
Yeah.
The James Webb Space Telescope is exactly that. It is 100 times more powerful than the Hubble telescope. Just look at the comparison of the sizes of their primary mirrors.
Wow.
And yet, James Webb's mirror is 113 kilograms, 249 pounds lighter.
What? I just need to pause it there and look at that. That is honestly incredible, because I feel as though everyone has seen just the Hubble telescope's images. They are honestly just everywhere and they are incredible. But then to see this here and go, what, it's about twice the diameter, which is 4 times as bigger, which probably gives it an optical range of, 100 times somehow. Wait, didn't he say it?
It is 100 times more powerful than the Hubble telescope.
Okay then, well that's exactly where I got it from. But no, 100 times more powerful than the Hubble telescope. Honestly, I can't wait to see some of the images that this thing produces. Because like I said, I've just always been blown away by Hubble, and even though that thing's like 40 years, 50 years old now.
And yet, James Webb's mirror is 113 kilograms, 249 pounds lighter.
Oh, and even that, the fact that it is lighter but 4 times as big. It's insane technology, and it's great to see that things are still getting better.
The telescope works in the infrared spectrum. The infrared radiation can penetrate the dust cloud and allow us to see the stars forming within. Additionally, Einstein's theory of relativity states that the space between objects in our universe expands, and so does light. As the light from the first stars and galaxies travels in our direction, its waves lengthen and the light becomes infrared.
Oh, all the way into infrared. I never even considered that. Wow. The fact that the earliest ones, if they are super far away, you're not going to be able to see on the visible spectrum because they're so stretched that they're going to be in the infrared spectrum. And so that makes so much sense as to why they would choose and design an infrared telescope, because like they said, its job is to be a time machine. And if you want time machine, honestly, you need to go all the way back into infrared.
Its waves lengthen and the light becomes infrared, also known as red shift. Every time you look up at the night sky, just know that there are many stars and galaxies, the light of which stretched and became invisible or too faint for you to see.
Wow.
So here's a question. How is the James Webb Space Telescope supposed to detect that light? It will be assisted by a huge mirror, which will increase the amount of collected light. The more light, the more detailed the image. The mirror is made with 18 hexagonal segments, each one 1.32 meters, 4.3 feet in diameter.
Whoa, I didn't realize it was that big. I would have thought that it would have been 50 centimeters, maybe 80 centimeters, but no, it's basically double that, or at least double that, at 1.3 meters each. No wonder it's so much better than Hubble, because I guess when you have 1.3 meters, not really to pi, but let's say close enough, just all over times 18, or probably even more. And so when it just takes all of that and then reflects it back into another central mirror and then back into the, I guess the sensor would be in the middle, no wonder you're just going to get these hopefully incredible images.
The mirror is made with 18 hexagonal segments, each one 1.32 meters, 4.3 feet in diameter.
Crazy.
This shape will enable the crew to fold the mirror on Earth and unfold it in space. Then, the focus of the mirror will be calibrated by shifting the various segments with an accuracy of 1 to 10,000, 1/10,000th of the thickness of a human hair.
Oh,
the light is
Wait, how do you design that? I mean, obviously someone did, but how do you design a fine focus motor? I can only assume to be able to do that. I mean, it makes sense that you need to, so nothing's just off, and especially when you're looking that far away, you're really trying to chase every last percentage of light you can get, so it has to be bang on, but I don't know how you design something that particular.
by shifting the various segments with an accuracy of 1 to 10,000.
Yeah, 1 to 10,000. 1 to 10,000 what? I don't know. He measured it against a human hair, which isn't really a measurement at all. But the fact that this thing has to be able to fold up in a massive way, but then also be able to just make absolutely minute movements is just, no wonder it cost $10 billion. And like I said, I'm surprised it only cost $10 billion.
The light is collected onto the secondary mirror. Then it is reflected and sent to the scientific tools. After it is filtered, it is then focused on the hypersensitive infrared detectors, at which point the photons are converted into electrical voltage.
Now, I'm not really sure what they are showing on the right here. Primary mirror, secondary mirror, fine steering mirror, and infrared detector. I get what each component is, but is that in the order and layer that it's actually laid out in? Because the light's coming in and it's hitting the fine steering mirror, but it's also called the primary mirror, so I don't know why there's a double up there. Then it's bounced back to the secondary mirror and then into the infrared detector, so I don't know why there's 4 components. I thought there was only 3, so maybe someone can let me know what's going on there.
The actual telescope is equipped with 4 tools. NIRCam is the telescope's primary imager in the near-infrared range. 10 sensitive detectors allow it to detect the light of the first stars and galaxies. In addition, NIRCam is equipped with chronographs. And what are they? Imagine that you're blocking the sun with your hand. By blocking the bright light, you can see the road ahead of you. A chronograph follows a similar principle. This function will allow researchers to see more faintly lit stars, galaxies, and even take photos of exoplanets. But NIRCam cannot show us everything we need to know about the physical properties of a planet. Is there water? Air? Impossible to say. Therefore, another tool called NIRSpec will be working with the same range.
What? I didn't realize it had so many layers to it. I mean, I guess it makes sense, just try and pack as much technology as you can into one piece of technology, if that makes sense, but no, that's insane. The fact that it can just hold up its hand to the sun and go, I don't really want to look at you, you're too bright, I want to look at everything around you. How would it possibly go about doing that? Because I can only imagine they can't just go and put something in the way like a sun visor or a hand. And so is it done through software or is it actually done through hardware is what I want to know.
Therefore, another tool called NIRSpec will be working with the same range.
Wow.
By studying the spectrum of light emitted by an object, we can tell its mass, temperature, and chemical composition.
As you do.
The atoms and molecules of an object leave their mark on the spectrum in the form of black lines. But to analyze the faintest light, the telescope has to stare at the object for over 100 hours, which is ages. But surely the scientists did not spend 10 years working in vain. To avoid wasting the telescope resources on a single object, the NIRSpec is equipped with a superpower to provide spectroscopies of hundreds of objects at once, which was achieved by developing a new technology called micro-shutter system. This system is made of 250,000 shutters that open and close.
Wait, I need to listen to that again. Was that 250,000
shutters? Which was achieved
shutters?
by developing a new technology called micro-shutter system. This system is made of 250,000 shutters that open and close.
What? Is this the bloody Koenigsegg Jesko or something? How have they gone and had 250,000 individual shutters working, I guess, in tandem to be able to block individual things out? Is that how they're doing what I was talking about before with the putting your hand in front of the telescope or whatever it would be? I mean, even the fact that it just has to sit and stare at an object, most likely with the sun involved somewhere along the line, for over 100 hours. Like if you pointed your phone's camera, or any camera for that matter, at the sun for 100 hours, I think you would end up with a black hole just being burnt out through the back of your phone. And so I wonder how they've gotten around that. I mean, I guess it's probably not their biggest problem. They're just adding a filter and it'll be okay. But even that, like, you know, every single thing adds up where you got to just fix all these individual problems before you just send it off, because once it's gone, and you just have to leave it out there forever.
If you ever observed the night sky in a town or city and compared it to what you can see at night in the countryside, you could probably tell the difference. It happens due to the high volume of light in the city. Therefore, the micro-shutter system will block the irrelevant light, allowing us to see the most faintly lit objects.
Crazy.
The light is then dispersed into the spectrum and sent to the detectors. How much light is there in outer space? A huge amount, and in order to capture only the relevant light, the telescope has to be constantly directed at different targets. This will be possible with the help of the Fine Guidance Sensor, FGS. Additionally, scientists from the Canadian Space Agency developed the Near-Infrared Imager and Stiltless Spectrograph, which also takes pictures and captures spectroscopies in near-infrared light.
Yeah, as you do, you just go and slam another piece of technology into there that you just developed, and I guess you hope it works after a lot of testing, but you've never actually been able to send it into space or / deep space. But I want to come back to this fine guidance system because you just kind of brushed over it.
This will be possible with the help of the Fine Guidance Sensor, FGS.
Oh, actually, it was a fine guidance sensor. I thought it was a fine guidance system. How is that a sensor if that's just kind of the motor unit? I don't really get that. And I wonder to what tolerance it has been built. I guess it would probably have to be really fine, probably similar to the mirrors themselves, because in a sphere you just have infinite radial points where you can just shoot out in any direction and all directions, and so to be able to pick out that second of a degree of a minute just in all of space, you would really need some fine focus, so that would be an engineering marvel in itself. I guess the entire thing, all its individual components, and every individual component is made of incredible individual components, down to the fact that they just have to be able to last for as long as they possibly can. It's like I said, you just can't go up and fix the thing, and so they just has to hopefully be up there forever. And I guess like Hubble's been up there forever, this one will hopefully just even have a longer life. And then I just want to go over this one again.
Scientists from the Canadian Space Agency developed the Near-Infrared Imager and Stiltless Spectrograph.
Stiltless spectrograph. Okay, so the near-infrared imagery. Okay, so I guess it's probably seemingly on the visible spectrum, but right on the cusp of the infrared system. So I guess you are probably getting the visible light that is shifted towards infrared at that point.
Which also takes pictures and captures spectroscopies in near-infrared light.
As you do.
But how do we deal with thick dust clouds that obstruct the view?
True.
Near-infrared light might not be able to penetrate them. And that's where the last tool comes in. MIRI is also equipped with a camera and a spectrograph, but it works in a different range of infrared light, one with longer waves, which can penetrate the thick dust clouds. Its sensitive detectors will allow us to observe the red-shifted light of distant galaxies, newly forming stars and comets.
Even through an entire dust cloud. Like, this isn't the kind of dust cloud that your car kicks up on a dusty day. No. This is a dust cloud that might be, I don't know, 500 million kilometers across, 2 light years across. I don't know. It's like these things are massive. The scale is just kind of unimaginable in space. And so it makes sense that light might not be able to pass through it. But the fact that you just go, oh, let's just shift it to a different part of the spectrum, and then we'll be sweet. We can just see through the entire thing as though it's an X-ray. Or I guess that's probably going the wrong way. You probably want to shift it more towards a radio wave if you really want to see through things. But either way, the fact that you just switch off one or you just go to another one, you go, oh yeah, now I can see it, no worries. And the fact that this all just came from it being sent up in a rocket, you know, all those G-forces, or that massive amount of vibration, then unfolded itself, then was able to be set up, and it still just takes incredible images.
The issue with MIRI is that unless this tool is cooled to 6.7 Kelvin or negative 266.5 Celsius, it starts capturing its own heat. So scientists developed an additional cooling system called cryocooler. In essence, it's a sophisticated refrigerator in which helium will travel along pipes, cooling MIRI to the right temperature as a result. But now we have a different problem. The sun, the moon, and Earth radiating heat. And as a solution for this problem, the engineers developed an incredible passive cooling system for the telescope, the Sun Shield. The size of this shield is 21 meters long and 14 meters across.
Whoa, 21 meters long and 14 meters across. I'm just trying to visualize the scale of this thing, because it had 18 1.3 meter hexagons, and then it's 21 meters long and 14 meters wide. So I don't think I really grasped how big it was. I mean, I guess I knew it was bigger than Hubble because it had to be kind of a newer, better technology. But to have just all those layers at 20 by 14 meters, I guess it's not a square or a rectangle, but it's still a lot of fabric. And so I wonder how much the whole thing weighs, because I think that is honestly some of the most impressive parts of all the space technology and development. It's just how they're able to make these things, but able to make them and just make them weigh nothing. I mean, the whole cooling system is definitely a hurdle that they would have had to get across, but I feel as though they've kind of had experience doing that with the ISS in terms of heat transfer and how to cool things that are kind of uncoolable, because I know in the ISS they can't have a traditional heat exchange just like a radiator with water, because that just freezes in little bursts and then everything breaks, and you can't have it the other way around because it'll cool too much, and so helium's just a perfect liquid in that state, liquid, to be able to just act and just be pumped through and just act as a cryo cooler.
The shield is made up of 5 layers, with space in between each layer of material so they can cool efficiently. Each layer is made from a special film that can withstand very high temperatures. This material is called Kapton. In addition, each layer is coated in aluminum, and the first 2 have an additional coat of doped silicone in order to be able to withstand even higher temperatures.
Like I said, every single thing is just like, as you do, why wouldn't you? I mean, at least in a case like this, sarcasm aside, you definitely have to be able to survive the just insane temperatures and environment that is space. But it's getting funky, and I guess therefore expensive when they start using elements or I guess compounds or whatever it be that I've never even heard of before. Kapton, like I said, I have no idea. Would it be a synthetic compound? Kind of like Kevlar if I had to make a random guess, but then it's also coated in aluminium and then also doped with silicon.
For the sun shield to be able to hide the telescope from the sun, the moon, and Earth simultaneously, the JWST has to be 1.5 million kilometers away from Earth. As a reference, the Hubble Space Telescope was only 547 kilometers.
That's right.
The James Webb Space Telescope will travel to a special location known as Lagrange Point 2. It is one of the 5 places in the solar system where gravitational forces allow the objects to remain in a fixed position relative to Earth.
And of course, we haven't even talked about the orbiting yet. That is just where it gets even more involved, because I guess you have to have the forethought to go, okay, we need a point within the next, let's say 100 years, where we just want to still be able to have contact with it and just put it a decent way away, but still have it in the same spot so we can point the same telescope up it from Earth and just be able to get and receive data from it. But then on the other end of the spectrum, kind of actually literally in this case, you'll just have a problem where you'll only be able to see Earth because it's giving off too much heat, let alone the sun. Earth is generally not considered a very warm thing. Most of our energy comes from the sun, but because they went and made the telescope 100 times more powerful, I guess sensitive than Hubble, then then all of a sudden Earth turns into a black body.
Remember how we talked about a folding mirror? Similarly, the sun shield and many other components will be foldable. This way, the scientists can fold the telescope and pack it into the rocket Ariane 5, which is the most reliable rocket capable of delivering the telescope into space.
I was going to say, why would you ever want to be packing the thing up? Surely you just did all the calibration, so surely you don't want to be just packing it up, just packing it away for the night and then unfolding it, recalibrating it to within, I guess, 10,000th of a hair every day, especially because he said it has to stare at a galaxy for 100 hours, and so I was going, what? Don't tell me they're packing the thing up, but no, it makes sense to be able to fit in the rocket in the first place, but then after that, just leave it unfolded, surely.
And now, let's talk about the most exciting thing. The possibilities of the James Webb Space Telescope.
Yes, here we go.
We already mentioned its ability to capture faint infrared light emitted by the first stars and galaxies. So what's next? Well, for example, you could spot the heat signature of a bumblebee at a distance of the moon with the JWST. Why should you care about a bumblebee?
Wait,
Did you?
hang on a second. If you told me at what time period do you think we'll be able to see a bumblebee on the moon, I would have said, I don't know, maybe 100 years from now, 50 years from now at the minimum. But no, we're able to make these things now. It just, like I said, it doesn't even sound real. And the fact that you have people like Elon Musk and Jeff Bezos that could buy, I guess, 50 of these things over and over and over again really just shows you that 10 billion isn't that expensive for the capabilities of this machine. I'm just blown away.
But why should you care about a bumblebee? Did you know that Saturn is not the only planet with rings? Uranus, Neptune, and Jupiter have them too. It's just that in the visible spectrum, their rings are dark and indistinct. Using the transit method in the infrared range, the telescope will be able to help us understand how the rings around these 4 planets formed.
Wow, hang on a second. I didn't realize that Jupiter also had them. I knew that, I think, Neptune or Uranus had one. And obviously everyone knows that Saturn has them, but I don't think I've ever seen any kind of imagery or even illustration of Jupiter having any sorts of rings. I just know that it has a lot of moons, but no rings. And so even that just shows you how it's realistically, in the grand scheme of things about what we're talking here, it is so close to home, and we just still don't even know that Jupiter has rings because we can't see it. And so then you just get infrared involved, and the entire night sky just starts lighting up completely differently to what you otherwise would see, and then I'm sure you get radio involved and the entire thing changes again. You go to X-ray and you get all these different things just building the picture more and more and more. So people go, oh, why are we building this thing? $10 billion, the amount of good that could have gone to on Earth. And yeah, okay, there's all these different avenues that money can go towards, but honestly, the amount of knowledge that is in space just sitting there waiting for us to collect, but we just don't know how to see it yet or don't have the technology, and then all of a sudden we just spend 10 billion and the entire night sky, like I said, changes. Why not?
Well, what about a detailed analysis of an exoplanet's atmosphere? The
Wow.
researchers are interested in the planets located in the habitable zone, which means they might contain water.
One.
By using the telescope, we can learn the chemical composition of those planets' atmospheres.
Crazy. It is just so detailed. Like I said, I cannot fathom how detailed this is. The fact that you can see a bumblebee on the moon and then a planet's just makeup based on the fact that it's refracting different lights. I forget the name of the experiment that was carried out, but he even showed in this video just the bar with it, you know, the individual black line, and that shows you what element is present. But generally an experiment like that is done in front of your own eyeballs in a lab where you just have everything on hand, not like 100 million light years away. And so like I said, it just to me sounds like science fiction. It doesn't sound real, but it's incredible and kind of inspiring that it is.
Scientist Michio Kaku thinks that the chances of encountering an alien civilization are quite strong. The telescope will be able to tell us more about the birth of galaxies, stars, and planets. It may completely change science as we know it. The universe keeps many secrets, but the James Webb Space Telescope should help us uncover these mysteries.
Well, that's a great way to put it. Almost like a translator of the entire universe. You know, all of these things are out there and you just need a translator between our medium, what we can see with our eyes in terms of visual light and visible spectrum, to all of these just secrets that are otherwise just hidden. Like I said, I've never heard of Jupiter having rings, but they're just chilling there and no one really knows about it because you can't see it with your own eyes. Let alone every planet, star, solar system, galaxy, supercluster, whatever it may be. It's all right there for the picking, hiding its secrets. Honestly, not even hiding its secrets. It's just, I guess it's physics. And like I said, we just need a translator just to be able to take what is up there right for the picking and just be able to transfer it back into a medium that we can actually see and comprehend and write down and study. And yes, the universe is just unimaginably big and it's just getting bigger, and our tiny brains can barely even pretend to comprehend the true scale of the entire thing. And so I'm so glad that I now know more about James Webb and hopefully the future prospects of the entire thing, because it certainly seems bright and it's got 4 ways to just perceive brightness. And so hey, it's certainly looking up, and let's just sit back and enjoy the ride, I guess. But anyway, in saying that, I guess I'm going to call it there. So thank you for watching this video. If you did enjoy it, feel free to do the YouTube algorithmic things down below. Also, if this is the first video of mine that you're watching, then make sure to go check out just any other ones I've done. Also, make sure to go check out the original video down in the description below, or hey, maybe even just want to consider subscribing so that you don't miss another one of these in the future. But all in all, have a good one and see ya.